Hello, everyone. Welcome to Friday ICANX Talks 2023. My name is Lan Fu. I'm a professor in physics from the Australian National University. So from last week, we kickstarted the excellent ICANX Talk 2023, and this is a reminder for the 5 excellent speakers lining up for our February talks. And tonight, we have the great pleasure to have Professor Tony Mikos to be our speaker. And of course, this is our panelist tonight, who I will introduce later on. So let me first introduce our speaker, Professor Tony Mikos. Professor Tony Mikos is the Louis Kandler Professor of Bioengineering and Chemical and Biomolecular Engineering at Rice University. His research focuses on the synthesis, processing, and evaluation of new biomaterials for use as scaffolds for tissue engineering, as carriers for controlled drug delivery, as non-trivial vectors for gene therapy, and as platforms for disease modeling. His work has led to the development of many novel biomaterials for medical applications. He is also the author of over 690 publications and inventor of 32 patents. Mikos is the members of the National Academies of Engineering, Medicine, and Inventors, and also the Chinese Academy of Engineering, the Academia Europaea, and the Academy of Athens. He has been recognized by many prestigious awards, which I don't have time to name them tonight. He's also founding editor and editor-in-chief of the journal Tissue Engineering. So, Professor Mikos, the floor is yours.
Well, can you see my screen?
Yes, perfect. Go ahead, please.
Excellent. Well, good day, everyone. Thank you very much for your very kind introduction. Excuse me just 1 second. Thank you again so much for your very kind introduction. I would like to thank the ICANX Talks for the great honor to present a virtual lecture. And I would also like to congratulate Dr. Ali Zhang of Peking University and the rest of the organizers of the ICANX Talks for their tremendous service to the scientific community in recent years. We all owe them a lot. Additionally, I would like to thank the moderator of my lecture, Dr. Lan Fu of the Australian National University, the panelists, Dr. Zumei Wang of Tsinghua University, and Dr. Kai Zhang of Sichuan University, and the ex-challenger, Dr. Zia Yang of Tsinghua University. Finally, I would like to thank Dr. Nicholas Pepas of the University of Texas at Austin for nominating me for this tremendous honor. Dr. Pepas was my PhD thesis advisor, and I'm most thankful to him for all his guidance and support over the years. I'm delighted to speak on biomaterials for tissue engineering and disease modeling and share with you our progress and vision in this exciting field. Biomaterials continue to play a very important role in the tissue engineering paradigm. They can serve as delivery vehicles for cells, bioactive molecules, and diverse signals in an effort to promote tissue formation and regeneration. Different biomaterial compositions have been investigated over the years, including synthetic polymers, natural polymers, ceramics, as well as metals. Moreover, different forms of biomaterials have been explored as dictated by the clinical need, including injectable biomaterials and 3D printable biomaterials, which will be the main focus of my lecture today. Injectable biomaterials allow for the delivery of combinations of cells, biomolecules, and materials with a minimal surgical intervention, whereas 3D printable biomaterials provide the architectural cues needed for the regeneration of various musculoskeletal tissues. Biomimicry has been the inspiration for the development of new or improved tissue engineering scaffolds. For example, the hierarchical structure of native bone from collagen fiber patterns to collagen fibers to mineralized collagen fibrils to nanohydroxyapatite, has inspired biomaterial scientists and engineers to invent new biomimetic strategies for bone scaffolds leveraging element-doped bioceramics, template-induced mineralization, recapitulation of micro and nanostructure, as well as stimuli-responsive bone scaffolds. For example, this year, in collaboration with Dr. Zhumei Wang and her colleagues at Tsinghua University, we reported in small structures the fabrication of artificial lamellar bone of centimeter size for the first time with a multi-scale cascade regulation strategy combining multiple techniques of molecular self-assembly, electrospinning, and pressure-driven fusion from molecular to macroscopic levels. The artificial lamellar bone that is composed of hierarchically assembled mineralized collagen fibrils highly resembles the chemical composition, multi-scale structural organization, and rotated plywood-like structure of natural lamella, thus achieving a good combination of lightweight and high stiffness, strength, and toughness. In another study published in Science Advances last year, in collaboration with Dr. Xingdong Zhang and Dr. Kai Zhang and their colleagues at Sichuan University, we reported the development of biomimetic and hierarchically porous polyether ketone-ketone scaffolds with a strategy combining sulfonation treatment and bone-like apatite deposition. Most excitingly, the biomimetic scaffolds proved to be osteoinductive and induce bone formation and regeneration ectopically and orthotopically in animal models by activating the cycling adenosine monophosphate and protein kinase A signaling cascade pathways. This is a remarkable example of the tremendous potential of biomimicry for development of new biomaterials for tissue engineering applications. In recent years, there has been significant progress with 3D printing and electric field-assisted techniques for the fabrication of three-dimensional scaffolds with designer architectures and geometry. These techniques include extrusion, electrospinning, melt electrospinning writing, and others, and allow the fabrication of homogeneous or heterogeneous structures and diverse morphologies, including the spatiotemporal presentation of biologics as needed for tissue engineering applications. Very importantly, these techniques allow the generation of compositional and structural gradients which are necessary for the creation of tissue interfaces. For example, in a study published in Acta Biomaterialia in 2019, we leverage extrusion 3D printing to fabricate dual ceramic and porosity gradient scaffolds of polyepsilon caprolactone and hydroxyapatite. The scaffolds exhibited a wide range of porosities and pore sizes and incorporated varied amounts of ceramic particulates, affecting not only their mechanical properties, but also their degradation characteristics. Interestingly, the compressive mechanical properties of the 3D printed scaffolds depended strongly on their porosity and were independent of their pore size, following power laws as indicated in this slide for the compressive modulus. Most excitingly, the generated architectural and compositional gradients resulted in phenotypic gradients of mesenchymal stem cells seeded into the gradient scaffolds. Confocal microscopy images of multi-layer cell scaffold constructs are shown in this slide, with mesenchymal stem cells lining the fibers of the scaffold with its pores designated with yellow asterisks. The differentiating cells exhibited a range of early and late markers of osteogenic differentiation, including mineralization, depending on the pore size and the beta-tricalcium phosphate content of the scaffolds. In addition to vertical gradient scaffolds afforded by layer extrusion 3D printing, we investigated the fabrication of horizontal gradient scaffolds by segmental fiber printing in an effort to produce anisotropic scaffolds with the complexity needed for tissue engineering applications. For example, as shown in this slide, we can print cylindrical scaffolds with a radial gradient of calcium phosphate content and porosity, resulting in gradient mechanical properties and degradation characteristics, and very importantly, in spatiotemporal presentation of degradation products, including calcium and phosphate ions. One of the main challenges associated with 3D printing techniques, such as extrusion 3D printing, is the retention of the bioactivity of any biomolecules incorporated at the high temperatures employed. In a recent study published in Bioprinting, we demonstrated that cartilage-specific peptides and bone-specific peptides conjugated to alkene-terminated polyepsilon caprolactone via click chemistry and 3D printed into osteochondral pattern scaffolds at temperatures as high as 95 degrees Celsius retain their bioactivity. This result is of tremendous value for the development of 3D printed scaffolds incorporating signaling peptides and necessitating the use of high temperatures for different tissue engineering applications. However, in another recent study reported in the Annals of Biomedical Engineering, when we 3D printed scaffolds of a biodegradable polymer impregnated with biodegradable polymer microparticles loaded with a potent osteogenic factor, bone morphogenetic protein 2, at high temperatures, we discovered that the bioactivity of any release growth factor was significantly reduced when the 3D printing was performed at 90 degrees compared to 37 or even 60 degrees Celsius. Clearly, proteins with a tertiary structure responsible for their bioactivity are more susceptible to high temperatures compared to peptides lacking a tertiary structure, and the delivery of bioactive proteins incorporated into 3D printed scaffolds at high temperatures remains a huge challenge in the field. The retention of the bioactivity of biomolecules loaded into 3D printed scaffolds has been the motivation for recent efforts in our laboratory towards the development of inks which can be printed at physiologic temperatures, thus preserving the bioactivity of any loaded biomolecules and retaining the viability of any encapsulated cell populations. In one such effort was reported in Biomaterials in 2021 and involves the development of colloidal inks of natural polymers, more specifically methacryloylated gelatin. Here, gelatin nanoparticles of varied intraparticle cross-linking density are also surface cross-linked with each other, forming structures of controlled degradation, kinetics, and swelling characteristics. In that study, we showed that we can reproducibly control the fiber diameter by varying the colloidal nanoparticle concentration in the ink and also the gauge index of the needle, and fabricate scaffolds of uniform fibers of diameters varying from 200 to 600 microns. Most importantly, we demonstrated that we could control the interparticle cross-linking density by UV radiation and therefore control the swelling properties of the fibers and the scaffolds and their degradation as needed for a particular application. The swelling of the scaffold may be preferred in certain applications. However, it may be detrimental in others, such as in osteochondral tissue engineering, where excessive swelling may lead to detachment of the scaffold from the defect. This work very eloquently showed how to independently control the intraparticle cross-linked density and therefore the release kinetics of any loaded biomolecules, and the interparticle cross-linked density and therefore the swelling and degradation of scaffolds. With a growing need for high-throughput manufacturing and screening, the need for modular biomaterials for biomolecule and stem cell delivery has emerged. Microparticles are a powerful platform that have demonstrated promise in enabling these technologies without the need to modify a bulk scaffold. In a recent study reported in Regenerative Biomaterials, we showed that by thiolating gelatin before microparticle fabrication, a versatile platform can be created that preserves the cytocompatibility of gelatin while enabling its modification post-fabrication for diverse drug delivery and tissue engineering applications. Extracellular matrices increasingly find applications as tissue engineering scaffolds because of the wealth of contained biochemical cues that aid in tissue formation and regeneration. In 2019, we reported in Tissue Engineering Part C Methods a technique to fabricate skeletal muscle decellularized ECM scaffolds with tunable physicochemical properties while retaining the pro-regenerative matrix components, and identified key steps for the successful production of electrospan skeletal muscle decellularized ECM without the use of a carrier polymer. In 2021, we reported in Science Advances the fabrication of electrospan scaffolds of decellularized skeletal muscle with tunable fiber alignment and cross-linking density in order to assess their potential to control bioblast growth and myotube formation. We tune fiber alignment by varying the speed of the rotating collector of the electrospinning system and the cross-linking density by varying the glutaraldehyde vapor exposure time. Here, RO stands for random orientation and AO for align orientation, and the numbers 1000 and 3000 designate the collector speed in RPM. Most excitingly, our studies showed that fiber alignment can provide the necessary framework to guide myoblast and myotube alignment. Moreover, we identified physical and biochemical properties that are necessary for myotube formation. For example, intermediate cross-linking promoted cell attachment and myotube formation, whereas 100% cross-linking hindered cell attachment by restricting access to free amines needed to support the biochemical cues from the ECM. The study demonstrated the huge potential for skeletal muscle decellularized ECM with tunable physicochemical properties towards achieving a therapy for skeletal muscle engineering. For the past decade, our laboratory has been part of the Armed Forces Institute of Regenerative Medicine, the mission of which is to accelerate regenerative solutions for the treatment of battlefield injuries. The main challenges we have faced for the regeneration of craniofacial tissues were that most of the defects resulting from improvised explosive devices are composite tissue defects, and the surrounding tissues are highly contaminated. In collaboration with clinical colleagues at the University of Texas School of Dentistry, we investigated a staged regenerative solution for the treatment of mandibular defects involving the implantation of a space maintainer and an in vivo bioreactor. Using advanced polymer chemistries and the principles of controlled drug release, we manufacture space maintainers that hold open the defect and prevent scar formation while allowing healthy soft tissue to grow over the space maintainer, and that locally release antibiotics into the facial wound, treating any local tissue infection that may inhibit normal tissue healing. Moreover, we design implantable in vivo bioreactors and leverage the body's own natural healing capacity to grow bone tissue in customized geometries and volumes. In a recent study, we combined the space maintenance technology with the in vivo bioreactor technology for the treatment of mandibular defects in a large ovine animal model. The in vivo bioreactors are chambers that can be inserted against the bone in parts of the body with a high regenerative capacity, such as the rib cage. We're able to shape these bioreactors to be of the same size and shape as the patient's facial defect. By filling the bioreactors with a scaffold capable of supporting bone regeneration, stem cells can be recruited locally into the bioreactor to fill the space with new bone tissue. After new tissue grows in the bioreactor, the space maintainer can be removed, and the new tissue, with shape perfectly matching the defect, can be transplanted into the defect for tissue healing. We investigated the regenerative capacity of different scaffolds within the bioreactors implanted against the periosteum of a rib in an ovine model, including autologous morcellized corticocancellous bone grafts and synthetic biophasic calcium phosphate grafts. These scaffolds generated new bone tissue because of the tissue inductive properties of the extracellular matrix, including the release of any sequestered growth factors for autologous grafts or those of released calcium and phosphate ions for synthetic grafts. Several studies from our laboratory and others have demonstrated that the high regenerative powers of the extracellular matrix, being essentially a carrier for tissue-specific inductive factors capable of promoting tissue formation and regeneration. In an effort to accelerate progress with the development of new bioinks, including extracellular matrices, for 3D bioprinting of cellular constructs, we and others also investigated the development of new high-throughput methods to evaluate new compositions of matter for their potential to 3D bioprint cell-laden structures in an effective and reliable manner. In 2020, we reported in bioprinting one such high-throughput method to screen different hydrogels such as collagen, gelatin, hyaluronic acid, and alginate for their ability to promote viability, proliferation, and differentiation of human mesenchymal stem cells. Such robust methods are highly impactful as they allow us to evaluate the biocompatibility of different bioink formulations very reproducibly, leveraging very small amounts of experimental biomaterials and stem cell populations over a short time period. For example, we investigated droplets with 1,000 cells and 10,000 cells corresponding to cell densities of 10 to the 5th and 10 to the 6th cells per milliliter, and showed that for both cell densities, collagen and gelatin-based bioinks exhibited higher cell viability by day 7 compared to hyaluronic acid and alginate-based bioinks, as assessed with a live death assay via confocal microscopy. In addition to bioinks themselves, different bioprinting additives can also enhance the differentiation of encapsulated stem cell populations, as well as the fidelity of bioprinted constructs. In a study reported in Biofabrication last year, we investigated the ability of calcium phosphate-based additives to enhance the osteogenic differentiation of mesenchymal stem cell-laden bioinks and the ability of glycosaminoglycan-based additives to enhance the chondrogenic differentiation of mesenchymal stem cell-laden bioinks for osteochondral tissue engineering applications. Moreover, we investigated the suitability of a wealth of bioinks for different 3D bioprinting modalities, including extrusion, inkjet, and digital light processing bioprinting, in an effort to develop a universal bioink for multiple 3D printing methods. Furthermore, we investigated different printability additives in order to enhance the rheological properties of bioinks, and more specifically, their shear thinning behavior, which is so critical for 3D bioprinting. For example, we showed that the inclusion of beta-tricalcium phosphate additives in bioinks promoted osteogenic differentiation of encapsulated human mesenchymal stem cells in a dose-dependent manner when cultured in 100% osteogenic media, and mixed media of 50% osteogenic and 50% chondrogenic media over a time course of 35 days. Additionally, the inclusion of hyaluronic acid, which was shown to enhance the chondrogenic differentiation of encapsulated human mesenchymal stem cells, was not associated with any mineralization when cultured in 100% chondrogenic media. In the same study, we investigated the printability additives xanthan gum and nanofibrillated cellulose. These additives have been shown to be biocompatible and also increase the viscosity in a plethora of studies in the past via the formation of chain entanglements or nanoaggregates. The increase of the viscosity is paramount to the stability of hydrogel structures printed in air and the retention of their three-dimensional architecture, and for this reason, their inclusion is desirable. We have shown that low concentrations of xanthan gum and nanofibrillated collagen increased both the viscosity and the degree of shear thinning of bioinks to a larger extent compared to that of the tissue-specific additives, hyaluronic acid and beta-tricalcium phosphate, as shown in this slide. Nevertheless, although the inclusion of printability additives can enhance the printability of constructs due to the increased viscosity of the bioinks in a dose-dependent manner, the increased viscosity presents a concern as it may be detrimental to the viability of any encapsulated cells for 3D printed cell-laden constructs, and therefore an optimization of the additive concentration may be needed for the desired outcome. For interfacial tissue engineering, such as osteochondral tissue engineering that involves a bone cartilage interface, the construct architecture becomes very important as it determines the extent of mixing locally and therefore the extent of cell signaling. In a study reported in Acta Biomaterials this year, we investigated the effect of multi-material architecture on the osteochondral integration of bioprinted constructs, which remains one of the big challenges in the field. More specifically, we investigated both gradient and segmented bioprinted fibers encapsulating human mesenchymal stem cells, leveraging a bone-like bioink, including beta-tricalcium phosphate additives, and a cartilage-like bioink, including glycosaminoglycan additives, and culture them within a porcine osteochondral explant of 4 mm thickness, including a 2 mm cartilage layer and a 2 mm bone layer for 3 weeks. At the end of the culture period, push-out testing was employed to characterize tissue integration, as well as biochemical and histologic analysis to characterize matrix deposition and cell infiltration across the interface. Photographs of gradient and segmented fibers produced via multi-material extrusion of a bone-like bioink and a cartilage-like bioink are shown in panels A and B in this slide. In both cases, a rhodamine dye was added to the bone-like bioink so one can visualize the extent of mixing at the interface. Clearly, significant mixing takes place in gradient fibers, whereas a sharp transition is evident in segmented fibers. Bright field and fluorescent images are also shown in panels C and D for gradient fibers, and E and F for segmented fibers. The distribution of the ceramic material included in the bone-like bioink across the interface is clear for both designs, as is the distribution of the rhodamine dye. Moreover, using scanning electron microscopy and energy dispersive X-ray spectroscopy, we further characterize the multi-material transition for gradient and segmented fibers. Scanning electron microscopy images at the top highlight the difference in the interface with suspended beta-tricalcium phosphate from the bone-like bioink pointed with red arrows. This difference is also shown in the energy dispersive X-ray spectroscopy images at the bottom, which highlight carbon, marked C, present throughout both the bone-like and the cartilage-like bioinks, and phosphorus, marked P, present primarily within the beta-tricalcium phosphate in the bone-like bioink. The details of the porcine osteochondral explant ex vivo model employed in the study are presented in this slide. Panel B shows the tissue harvesting and osteochondral defect creation processes, resulting in a 1 millimeter diameter cylindrical osteochondral plug with 4 millimeter of length, with both explant and plug cultured in well plates with osteochondral medium until study initiation. Panel C shows a demonstration of the bioprinted fiber insertion technique before and after swelling occurred to fill the defect diameter. Tissue integration was assessed with push-out testing of gradient fiber groups marked G Fib, segmented fiber groups marked S Fib, and osteochondral control plugs marked OC plugs. At different time points, samples were split into two tissue sections, the bone section and the cartilage section, and the bone tissue integration and cartilage tissue integration were assessed from measurements of the peak force and total energy for each section. The bone tissue integration for both fiber groups was different from the natural tissue group, most probably due to differences in their texture compared to that of trabecular bone. Most importantly, both gradient and segmented fiber groups had similar cartilage tissue integration as the natural tissue group, and also the gradient fiber cartilage integration increased by day 21. These exciting results corroborate with biochemical data of significant sulfated glycosaminoglycan deposition over time in the cartilage section of the gradient fiber group, which was higher per cell than the segmented fiber group. Histological analysis of cross-sections of the entire model with hematoxylin and eosin for extracellular metrics and cytoplasm, and nuclear fast red and Alcian blue for glycosaminoglycans revealed migration of cells into the fiber chondral boundary and the deposition of extracellular metrics locally contributing to fiber tissue integration at the cartilage layer, as shown in this slide for a segmented fiber design. And in this slide, at higher magnification, at the fiber chondral boundary, which with arrows indicating cellularity and regions of matrix deposition for the left and middle images. The right image shows a cross-section stained with von Kassa for mineralization and calcium content, with arrows pointing to darker regions of staining indicating mineralization. The histology results further support the fiber push-out testing data of similar cartilage tissue integration as the natural tissue group. At this point, I would like to shift gears and focus on injectable biomaterials, and more specifically on thermogelic polymers. Thermogelic polymers undergo a hydrophilic-hydrophobic transition at their lower critical solution temperature, or LCST. They are liquid at temperatures below their LCST and gel at temperatures above their LCST. These polymers with LCSTs between room temperature and physiologic temperature have been investigated as part of injectable formulations for diverse biomedical applications, including tissue engineering. One popular thermogelic polymer is polyanisopropyl acrylamide, which has a low critical solution temperature around 32 degrees Celsius. In 2019, we reported in Science Advances the synthesis of new modular, tissue-specific and biodegradable hydrogel cross-linkers, abbreviated PDBT, incorporating sulfhydryl termini for chemical cross-linking, polyester segments for hydrolytic degradation, and alkene moieties for aqueous click binding of bioactive molecules, including hydrophilic peptides, hydrophobic peptides, and large glycosaminoglycans, as shown in this slide. These tissue-specific cross-linkers were leveraged for the development of dual thermally and chemically gelling injectable hydrogels based on poly and isopropyl acrylamide and conjugated with tissue-specific biomolecules. Specifically, thermogelling copolymers of N-isopropyl acrylamide with glycidyl methacrylate were synthesized to allow for chemical gelation via a thiol epoxy reaction. We demonstrated that a dual gelation mechanism ensures the formation of a hydrogel and prevents syneresis, which is so important in tissue engineering applications. In a follow-up study published in Acta Biomaterialia in 2021, we investigated osteochondral tissue regeneration by implantation of bilayer cell-laden hydrogels of a cartilage-specific hydrogel and a bone-specific hydrogel functionalized with a chondrogenic peptide and an osteogenic peptide, respectively, and encapsulating mesenchymal stem cells in a rabbit osteochondral defect model, as shown in this schematic. After 12 weeks, mesenchymal stem cell-laden hydrogels with a chondrogenic peptide sequence produce higher histological measures of several markers of osteochondral tissue regeneration, including overall defect filling and cartilage surface regularity compared to both non-cell-laden and non-chondrogenic hydrogels. Very excitingly, the results of this study establish the utility of bioconjugated stratified hydrogels for repair of the osteochondral unit. In another study published this year in the Journal of Biomedical Materials Research, Part A, we investigated the effects of charge and lower critical solution temperature on cellular infiltration and tissue integration in a porcine cartilage explant model. For this study, we synthesized dual thermally and chemically gelling macromers of N-isopropyl acrylamide, glycidyl methacrylate to enable chemical gelation, acrylic acid to fine-tune the LCST, and dimethyl gamma butyrolactone to raise the LCST over time as the lactone ring hydrolyzed. More specifically, thermogelling macromers possessing 0, 5, and 10% dimethyl gamma butyrolactone were synthesized. Additionally, 3 model peptides were designed to impart charge in the hydrogel via conjugation to the cross-linker. The positively, neutrally, and negatively charged peptides K4, Z-terionic K2E2, and E4, respectively, were conjugated to the modular cross-linker, and the hydrogels were evaluated for their thermogelation behavior in vitro before injection into the cartilage explant models. A hydroxyproline spacer was added between all charge-bearing groups to prevent beta sheet formation of the peptides. Also, a tyrosine amino acid was included in its peptide, flanked by glycine spacer on either side to allow detection and quantification of the peptides. The 3 charged peptides were combined with a PDBT cross-linker via Zeit-alkene click conjugation at room temperature in aqueous conditions using a cytocompatible and water-soluble ruthenium catalyst as shown in this slide and characterized with proton NMR. Then positively charged neutral or negatively charged hydrogels were fabricated bearing variable charge and dimethyl gamma butyrolactone content to investigate the effects of charge and lower critical solution temperature on cellular infiltration and tissue integration in an ex vivo porcine tissue explant model. The results were very unexpected and most exciting. Although one would have expected better tissue integration with positively charged hydrogels due to electrostatic interactions, taking into consideration the negatively charged glycosaminoglycan component of the cartilage extracellular matrix, the push-out testing data indicated the opposite, that is significantly enhanced tissue integration with negatively charged hydrogels compared to positively charged and neutral hydrogels. Moreover, the negatively charged hydrogels containing 5 and 10% dimethyl gamma butyrolactone demonstrated cellular infiltration and cartilage-like matrix deposition after 21 days via histology, which was not evident in any other group. Excuse me. For example, the arrow at the bottom right of the right panel points to areas where cells have infiltrated and are remodeling the hydrogel space. Collectively, our data demonstrate the importance of both hydrogel charge and lower critical solution temperature over time in the success of cartilage tissue engineering strategies. Specifically, negative charge is demonstrated to be important in allowing the initial diffusion and transport of nutrients, extracellular matrix components, and proteins from the native tissue into the hydrogel, as schematically shown in this slide. Second, the hydrogel lower critical solution temperature over time is demonstrated to be important as initial hydrophobicity promotes protein absorption, which encourages cellular infiltration and adhesion. As the network becomes more hydrophilic, continued diffusion and transport across the hydrogel tissue interface occurs, which contributes to the success of these strategies. In another study reported in Bioactive Materials last year, we adopted the same dual gelling injectable hydrogels for use as dual gelling inks for high-resolution extrusion printing of multi-layered structure on the tens of micrometer scale with a thermoreversible poloxamer support bath. Here, as shown in the schematic of this slide, the ink is cooled down to 12.5 degrees Celsius and then extruded into the support bath heated to 37 degrees Celsius, where it immediately undergoes thermogelation. It is then incubated for 2 hours, while covalent cross-linking completes before being removed and placed into excess water to wash away any remaining bath material. The support bath maintains the structure of the ink in a hydrated, heated environment, ideal for cell culture, while the ink undergoes rapid thermogelation followed by a spontaneous covalent cross-linking reaction. We demonstrated that the rheological properties of both the dual gelling ink and the poloxamer support bath affect printability. For example, in addition to shear thinning behavior, the support bath concentration also affects its yield strength, calculated from data in panel D, which represents the resistance the bath offers to ink extrusion and also serves as a metric for the bath's ability to self-heal. Moreover, as shown in panel E, the recovery of different baths following oscillating magnitudes of strain was measured to determine how well the baths maintain their mechanical properties following repeated exposure of high stress, which occurs when the printing nozzle moves through the bath repeatedly. We further demonstrated that the dual gelling ink concentration and the support bath concentration, as well as the nozzle diameter, collectively affect printability outcomes, including the fiber diameter and the shape and area uniformity of printed scaffolds. The high fidelity of the printed structures was visualized with the addition of rhodamine to the ink and can be appreciated in the top right images. The fiber diameters measured varied from 80 to 200 microns, which presents very exciting opportunities in tissue engineering. Most importantly, we demonstrated the ability to leverage dual gelling inks for 3D bioprinting of cell-laden scaffolds with high cell viability. First, leachables from the dual gelling inks were cytocompatible with a cell line in vitro at different dilutions as shown at the top of the slide. Second, encapsulated cells remained viable after 24 hours as visualized at the bottom imaging, with live cells stained green and dead cells stained red. Continued efforts in our laboratory focus on 3D bioprinting of gradients of cell phenotypes in an effort to engineer complex anisotropic tissues. Undoubtedly, cell viability and differentiation are equally important as printability outcomes. Interestingly, factors affecting print resolution, such as ink concentration and bath concentration, also affect cell function due to osmotic effects. Also, nozzle diameter, which directly controls fiber diameter, influences the shear stresses exerted on encapsulated cell populations, which can affect their viability and phenotype. Clearly, the relationships between a complex web of factors during printing will need to be elucidated before the translation of 3D printable biomaterials to the clinic. Advances in tissue engineering in recent years have also propelled the growth of a new field of tumor engineering. We and others in recent years, we built on our experiences with 3D culture technologies to develop models of tumors in an effort to investigate and better understand cancer biology, and also to develop models, reliable models, to screen different chemotherapeutics. The complexity of these models includes both biological elements and also physical elements. Biological elements and include different cell populations, including stromal cells, immune cells such as macrophages, lymphocytes, but also physical elements, including shear stresses, mechanical effects, interstitial flow, fluid changes, and others. So over the years, this has been the focus of many investigators in an effort to understand which of these elements affect the phenotype of cancer cells and also the response to different chemotherapeutic drugs. The goal here is to develop 3D models that will have the high throughput capacity of monolayer cultures, but also the accuracy of in vivo models, such as the patient-derived xenografts. Monolayer models are very inexpensive, are very high throughput. However, 2D biology cannot recapitulate the complexity of three-dimensional tissues. At the same time, in vivo models are very accurate. However, they're not very high throughput and they're very expensive. So our goal and the goal of the community within the growing field of tumor engineering has been to develop models at the interface of the monolayer and in vivo that capture the complexity of in vivo models with the high throughput characteristics of the monolayers. In a recent study that we reported in Acta Biomaterials, we investigated how the mechanical responsiveness of a substrate can affect the phenotype of osteosarcoma cells. So we coaxially electrospan fiber scaffolds are made of a poly epsilon caprolactone core and gelatin sheath, a gelatin shell, resulting in mechanical properties of the scaffold scanning for orders of magnitudes, as shown in this slide. And we investigated how the mechanical responsiveness of the substrate can affect the phenotype of the cancer cells. More specifically, we focus on YAP and TAZ, which are downstream effectors of the HIPPO pathway and are involved in mechanotransduction. Very interestingly, we showed that the mechanical properties of the substrate can affect the nuclear to cytoplasmic ratio of both YAP and TAZ in a dose-dependent manner. And these values were comparable to the ones that were able to measure from biopsies of cancer patients. Very interestingly, the nuclear to cytoplasmic ratio for two-dimensional cultures was outside the range observed in cancer patients, which support the notion that we cannot capture the complexity of three-dimensional tumors with two-dimensional monolayer cultures. Very interestingly, we reported how the exact nuclear to cytoplasmic ratio for YAP and TAZ can be used as predictors of clinical outcomes of cancer patients, which supports the value, the huge value of these tumor models. A growing field that impacted several diverse technologies in recent years is machine learning. In 2020, we reported in Tissue Engineering Part A how machine learning can guide extrusion-based 3D printing of tissue engineering scaffolds. We showed how machine learning algorithms can leverage data on material accuracy and machine precision for different material compositions and printing parameters to predict the quality of the resulting print. Furthermore, we demonstrated the enormous value of machine learning for designing new or improved scaffolds for tissue engineering applications. Clearly, advances in machine learning will propel progress in tissue engineering in the future. In closing, I would like to thank again Dr. Ali Zhang and the ICANX talks for this exceptional honor. I would also like to acknowledge the generous support to my laboratory by several funding agencies, and most importantly, to express my sincere gratitude to my collaborators for their inspiration and my students for their hard work. Thank you very much.
Thank you very much, Professor Mikos, for such a so many fascinating results. So let me now introduce you our panelists and then inviting them to the stage. So our first panelist tonight is Professor Kai Zhang from Sichuan University. Dr. Kai Zhang is a Deputy Director of the Institute of Regulatory Science for Medical Devices and the Professor of School of Biomedical Engineering and the National Engineering Research Center for Biomaterials of Sichuan University, Chengdu. And Professor Zhang is a Fellow of American Institute for Medical and Biological Engineering, a Fellow of Biomaterials Science and Engineering of the International Union of Science Societies for Biomaterials Science and Engineering. He's also a council member of the Chinese Society for Biomaterials, and also he's a member for many advisory committees, different committees. And Professor Zhang's research interests include regenerative biomaterials and medical devices and regulatory science for medical devices. He has published many books and very high-level publications, as well as many Chinese, US, and EU patents. He also has quite a few technologies being commercialized into medical products. Professor Zhang also serves as editorial members for many journals, including Bioactive Materials, Journal of Biomedical Materials Research, Part B, and so on. Our next panelist is Professor Xuemei Wang from Tsinghua University. She is a professor at the School of Material Science Engineering, Tsinghua, and she obtained her PhD degree from Tsinghua University, and then she did her postdoc fellowship at the University of Rochester and also MIT in 2005 to 2008. Then she started her professional career in Tsinghua from 2008. Her research is mainly focuses on biomaterial-based multimodal tissue engineering strategy for tissue regeneration. She has published more than 170 SCI papers and filed 9 patents and also written few book chapters and books. She is executive member of the Chinese Society for Biomaterials and served as the co-editor-in-chief of Tissue Engineering Part C and editorial member of Frontiers of Material Science, Regenerative Biomaterials, and Material Research. She has got received many also outstanding awards, which I won't have time to name it today. So welcome, Professor Xuemei Wang. Also, we have our ex-challenger tonight, Jia Yang from Tsinghua University. She is currently a PhD candidate at the Institute for Regenerative Medicine and Biomimetic Materials from the School of Materials Engineering, Tsinghua, and is supervised by Professor Xuemei Wang. Her research interests include the construction of biomimetic tissues by 3D engineering technology and the evaluation of tissue regeneration and repair effects. So let me just invite all panelists tonight on the stage. So what I'll do is the first, as usual, let me invite our ex-challenger, Jia Yang, to ask the first question.
Okay, thank you for such a great talk. It's very instructive for us. And now I have 2 questions. What are the current challenges in modeling tumor microenvironments and how to address it to improve the accuracy of the tumor model?
Thank you so much for the excellent question. I think the big challenge with the tumor microenvironment is what to identify the elements that are responsible for the phenotype of the cancer cells and also for their response to different chemotherapeutic drugs. As engineers, we're trying to analyze the complexity into the individual components, trying to understand what is the contribution of each component, and once we identify the most important components, to synthesize those components into a model that will capture the necessary complexity of the tumor microenvironment.
Okay, thank you for your excellent answer. The second question, what do you think about the prospects and limitations of artificial intelligence and machine learning in biomaterials design and tissue engineering?
That's another excellent question. I mean, artificial intelligence has infiltrated all aspects of science, and artificial intelligence provides the tools that can help us make progress in many areas, including tissue engineering and regenerative medicine. So artificial intelligence and machine learning can be used as predictive tools to design new material compositions, new processing parameters, but also machine learning tools can be used to extract information from the wealth of data that is available to scientists nowadays, and use machine learning to establish relationships between different components of the stem cell microenvironment, for example, over the tumor microenvironment, something that scientists have not been able to understand and discover with other tools. So there's a great potential, and we're going to see a lot of progress in the coming years with the impact of artificial intelligence and machine learning and tissue engineering. Thank you.
Thank you for your answer. I have no more questions.
Thank you, Jia. So now let's just invite our panelists. Please go ahead. Professor Zhang and Shemei, do I have a question? And also at the same time, I'd like to let you know that we also have our good friend, Professor Nicolas Pepas, actually also in our studio. So please also feel free to jump in and ask questions, Professor Pepas. So Professor Zhang, maybe you have a question. Please go ahead.
Yes. Well, Nick, I'm sorry, Tony, the very good talk. I learned a lot. One thing, I think we made a lot of progress in the past many years is for the translation of tissue engineered medical products. It was not included in your talk today, but please, can you comment on the progress for the tissue engineered medical products in the field? So the young scholars, students, they will contribute more for the future translation and future products. Thank you.
Thank you, Kai. That's an excellent question that I think it's important to address in this audience. Translation is very important. I think the mistake that we all made in the past was that we start thinking about translation and the completion of a research project. I think translation starts with the conception of a project, and one will need to think about translation when one designs scientific experiments, because the results of these experiments will be included in an FDA submission or a submission to a regulatory agency, and it's very important that appropriate things are taken into consideration. 10 years ago, 20 years ago, everybody talked about the huge value of collaboration between scientists, engineers, and clinicians. Yes, this is very important for basic scientists and engineers to discuss with clinicians the clinical need, the applicability of the new technologies. But nowadays, I mean, for the translation, it's very important to engage also business people, because business people will be involved with the development of, with the commercialization strategies, will be involved with securing any intellectual property that results from the studies. So I think tissue engineering in many ways, I mean, is a convergent science, and to make progress, we need to engage people from all parts of science, business, and the healthcare to develop strategies that will be acceptable to the community. Thank you very much for bringing that aspect.
Thank you.
Okay, more question?
Yes, I do have another question. You know, recently we heard the news that FDA is getting rid of the animal studies for the drug screening. So while you are sharing, you know, the tissue engineering for the tumor tissue engineering, I'm wondering the engineered tissues or what we are developing while researching can one day to help to minimize the animal tests for biomaterials, for medical devices. Can you comment on that, please?
Yeah, that's a very interesting point, and I cannot generalize. I mean, the decision that the FDA made and the conditions at which animal experimentation may be restricted. I would comment and say that animal experimentation is very well monitored and supervised, and in order to conduct animal studies, the highest standards must be followed, and also the need for animal experimentation must be fully justified. I would agree that there is no animal model that can capture the complexity and physiology of humans. However, I mean, animal models may be needed, or models in general may be needed as preliminary studies before clinical studies are initiated. I must say, I mean, going back to the previous question about the impact of artificial intelligence, this is an area that artificial intelligence can impact the translation of any technologies to the clinic by providing the tools that will help us optimize or expedite or studies that will minimize animal experimentation or eliminate animal experimentation as needed for a particular application. Again, I will not generalize, but I must say, I mean, we are at a stage now that we have the necessary tools that will help us better design and extract more information out of any study.
Great, thank you. Thank you.
Jermaine, please.
Hey, thank you, Professor Mikos. Many thanks for your excellent lectures. And thank you very much for sharing so many awesome works and the recent progresses in tissue engineering and also applications in tumor models. So I also have two questions. One is for Professor Zhang's question. I also pay more attention on clinical translations of tissue engineering product. So how do you think if we need to adjust the endpoint of tissue engineering product in clinic? That means if we focus on complete regeneration, maybe it's very hard to put into clinic. So do you have some advice to speed up the clinical translation of tissue engineering products? This is the first question.
Yeah, thank you very much. That's an excellent question. I think the endpoint, it's very important. And obviously the endpoint, I mean, needs to take into consideration the particular strategy, especially the presence of any synthetic natural material that is implanted into the body, a material that is foreign to the body. So the degradation kinetics of the material, I mean, it's very important because in the biomaterials field, many times, I mean, problems with implantation of biomaterials were due not really because of the materials themselves, but because of the degradation products. So having an endpoints that will help us assess not only the effects of the implantation and the presence of the biomaterial, but any effects during the degradation and following the degradation of the material, this will be very important. At the same time, I mean, we need to assess the time for tissue remodeling. Tissue formation is very important, but all tissues in the human body undergo constant remodeling. And we have to make sure that the particular strategy, the particular material or combination of cell does not adversely affect the tissue remodeling process. So material degradation, tissue modeling, remodeling, these are all very important consideration. That obviously, I mean, depending on the regenerative capacity of the tissue, can vary. There are tissues that have very high regenerative capacity, so the endpoint may be an early time point, but other tissues that the regenerative capacity is very low, so I mean, the endpoint may be a longer one.
Thank you. Thank you. Another question about the biomaterials design. When we design the biomaterials, how do you think the design criteria for regenerative biomaterials? So we also want the best materials, right? To optimize the biomaterials parameters like compositions, mechanical properties, and topographies, and some biologic ligands. So how do we to decide the most important parameters to design biomaterials, to optimize biomaterials? As the microenvironment for tissue generation, biomaterials can be considered as stem cell niche and immune modulation environment or anti-aging environment, and so on and so forth. So how do you think that?
That's really an excellent question. And there are many different ways that I can address this question. First and foremost, the material must be biocompatible. In that is, the material must perform specific function with an acceptable host response. The material must support the formation and regeneration of the tissue. The material must be conducive or inducive to tissue formation and regeneration. These are all characteristics that are very well understood in the tissue engineering community. However, I will use this opportunity to emphasize again the point that was raised earlier about the translation of biomaterials in tissue engineering strategies. And that is taking into consideration, yes, all the physical-chemical properties of the material, all the biological characteristics of the biomaterial. This is very important. But what is equally important, if not more important, is the translation of the biomaterial. So we don't need to introduce the unnecessary complexity that will not contribute to the benefit and the value of the biomaterials. So we now, as a community, know a lot about the regulatory process. I mean, how the regulatory process can be expedited, how the addition of some elements into the biomaterial or into the strategy can delay or increase exponentially the cost of the translation of the biomaterial. So the best way that I can answer your question, which is an excellent question, is that not only physical, chemical, and biological considerations need to be taken, but very importantly, the translational aspects and the regulatory aspects of the biomaterial and the tissue engineering strategy.
Great. Thank you. So as you just introduced earlier on that Professor Peppers was your PhD supervisor. So I wonder whether the PhD supervisor has some hard question to ask the former student.
Thank you very much, Dr. Fu. Tony, this was an exceptional talk. I mean, I keep hearing the latest things you do, but the way the whole thing was presented today, I'm really at awe of what you have done at Rice University and with collaborators in China and everywhere else, Europe. At the same time, of course, it makes the rest of us, especially the young generation, very concerned. I mean, how can we do as much and more in so many years? But I do want to come to one question and one comment by Kai. The question is, I come from a materials background before I became a biomaterials person. So I'm always worried that, and I don't doubt your work, but I always worry all these 3D printed systems. Do they leave any toxicity behind? Do they leave any unreacted monomer? There are applications where we are talking about parts per billion being toxic. And here I have people, this week I had two marvelous speakers in my department. They were talking about 3D printing inside the body by injection and then 3D printing inside the body. And when you ask questions about what happened to the monomer, you don't get the satisfactory answer. So is there anything you can say about that?
That's an excellent point. Excellent point. I mean, and I think because of this, which is hugely important, I always emphasize that what is really regulated is not the biomaterial, is not the medical device, it's the process. So I think it's very important for people to realize that any unreacted monomers, any catalysts that are left behind, even in a very, very small, minute amounts, can cause a huge negative effect. And thankfully, this is something that regulatory agencies pay a lot of attention. And again, a material in an ideal form without any unreacted monomers, without any remaining solvents or catalysts, may be purely highly biocompatible. But what the biomaterials field has learned over the years is that the problems arise from these impurities, from these unreacted monomers that can be catastrophic in many ways. And we have, unfortunately, many examples in the biomaterials community of medical devices that failed eventually because of small changes in the processing that introduced some minute amounts of chemicals that had a very negative effect. Thank you very much. That's an excellent point.
Thank you. And the second
comment on that?
Go ahead.
Yes, Nick, when we think about this, the very successful, one of the earliest successful biomaterial product is polymethyl methacrylate bone cement. That was in situ cured in the body. And it was problematic with the monomer release. And but it was the product was proved, was demonstrated to be safe and effective. And so I think Tony made a very good comment. It's all about the control. It's design control. It's quality control. So when we do research, you can play anything you want. But when you develop a product, a medical product, it's always about safety and efficacy. So put that on top of all the research work, all the product R&D. So that's my comment. Thank you.
Very good. The second and the last comment is based on what Kai said. When we heard the news a few weeks ago that FDA was going to start approving, or at least considering approving, products without animal studies, some of us who are supporters of animals, very strong supporters of animals, were out in the street saying, finally, because we find, with all due respect, Tony, and I know you do your work incredibly well, but not all universities are like rice. I have heard of cases of scientists who say, oh, I have an idea, give me 5 rats, and I will do the experiments. And there are sometimes that they will do experiments that maybe they haven't gotten the approval to do them. So I want to make sure that we do animal experiments after, as you have developed the material, you have developed the scaffold, you know what you're doing, and you will not get them right from the beginning. For me, the life of an animal is sacred. And as long as I live in the next 20 years or 10 years or 5 years, I'm going to be fighting for that. I don't know if you want to say anything.
Well, I fully agree. And actually, this is one thing that everybody becomes aware the moment they initiate any animal experimentations. The 3 R's, and the first R is reduce. Can you reduce the number of animals or eliminate, the use of animals altogether? I fully agree. And I think if we can make progress and develop safe and effective medical devices for the betterment of health care without animal experimentation, I'm a big supporter. There's no question about that.
Yeah.
Thank you.
Yeah, Tony, let me also comment on that. My question actually is about the application of the tissue engineering. So, lab on chip and engineered tissues, and we can use them as models, as phantoms, to demonstrate the medical product safety and efficacy without using animals. And so that's actually is, I think, FDA is trying to push, is this is actually part of what I'm now very interested in is regulatory science. So can you develop new standards, new models, new tools to demonstrate the safety and efficacy of new products, especially the innovative medical products you have never heard or we have never seen before? And so that's my question about is, or my comment is on the future applications or more applications of what we can engineer ex vivo or in vivo from the tissue engineering approach. Thank you.
Well, Kai, you raise a very, very valid point. And I think the FDA made one decision, but really the responsibility is upon all of us, is upon all of the scientists, the engineers, the clinicians. I think what I envision as the next step to make progress is the development of reliable models, in vitro models, that will help us predict the in vivo physiology and the in vivo response of different drugs. So I envision organizations such as the ASTM, the ISO, to be involved with the development of standards that the FDA will listen, will accept, and the FDA will accept to the consensus opinion of the scientific community that can be used instead of animals. So this is now, as a community, we're all responsible for the development of such reliable models to really make progress.
So as a person who not actually really work in the field, and I feel really overwhelmed by the discussion here, because to me, I as a general user, maybe with those kind of things, we will expect all this new research, new medical device will be going through a very rigorous regulation process and testing with time and with animal with real clinical trial. But isn't that the case? It's rather some of the medical things can really go through translation really quick, accelerated without actually even animal test. Is that true?
Well, I can answer the question. It's very hard to tell. I mean, it's obviously, as Professor Pepas indicated, that's the wish of the entire community. I don't think there is anyone, any responsible scientist, biomaterial scientist, or tissue engineer who would be advocate of animal experimentation. No. I mean, animals in the past have been used because people realize the value in the translation. If now, I mean, we can eliminate that with new tools, I mean, yes, I mean, everybody is very supportive, and everybody needs to work very hard to demonstrate to everyone else that these models can be used safely, because people want to know, I mean, when they have a medical device implanted, is it going to be safe? Is it going to be effective? They're not going to ask other questions. It's their health. I mean, and that's the things that matter to them. So we're very passionate about medical devices, about the impact that can have in health care, but also we're very concerned and very sensitive to animal experimentation. And if we can reduce and eliminate, I mean, that would be wonderful.
Yeah, thank you very much, Dr. Fu. This is a very good comment. I never meant to say that something will go in a patient, in a human, before it has been tested. But what I wanted to say is, don't kill animals, don't use animals long before you have finished the cell studies and identified that indeed you have something that is non-toxic to animals. And then that's what I'm trying to say. So the FDA decisions in the United States a few weeks ago are a big step for us who protect animals. And we want to make sure that animals are not going to be used by a graduate student so that he or she can get a PhD thesis. That's the wrong idea. It has to be, I mean, you can still do a nice PhD thesis without animals.
Exactly.
And make us think. But using an animal just because of that, I don't like that. Period.
Yeah, let me also comment on that. I mean, Tony did a wonderful talk today. I mean, so use his approach. We can probably 3D print, or we can tissue engineer a very good blood vessel, and it's alive or similar to a real animal. In vivo, and then we can test it. We can use that as a model to test the new products, and without going through the animal test. Well, the condition is if this engineered tissue has been demonstrated to be feasible, to be valid. And Tony, I do believe it's very promising to achieve that. Right, and in that tissue engineer can help, and that's actually one of the things I think we can work on that to promote.
Absolutely. I mean, I fully agree with you, Kai, and I must say, I mean, that presents wonderful opportunities for young scientists. I think the new emerging fields that combine advances in biology, in computer science, and materials science, I mean, for the development of organ on a chip or other models that will have high predictive value. I mean, these are wonderful, wonderful opportunities for young scientists to enter the field and to use new tools and new logics that can help us can even expedite the development of new medical products.
That's great. Actually, you touch on this very interesting point, talking about young scientists and working a very multidisciplinary project like yours. as hinted by Professor Peppers, you said like you are a material scientist, and then assume that when he started with you, when you started with Professor Peppers, you started with material science, and then slowly you can see the breadth of your research covering so many fields. So what are the advice you have for young scientists that really starting from a small field and now trying to get in such a big field? What kind of skills and advice you would like to give them? Like you should advise them to gain, I mean, in terms of skill sets.
That's an excellent question, and I have to be very careful how I respond, having my PhD advisor in the audience. But if there is something that I can say safely, I mean, based on my experience, without getting into details, emphasizing the fundamentals is very important. It is very important because we don't know what will be the technological needs of the future. However, if we have a very strong foundation in the basic sciences, in chemistry, in physics, in biology, in computer science, that will help us solve any future problem, any technological needs, societal needs. And I think what is very important for people in this field is to be passionate about the mission, I mean, of the field. And the mission is to improve healthcare. We're not in this field because we want to publish a great paper or to make money. We're in this field because we are passionate about the betterment of health care and the impact that we can have on fellow human beings.
Excellent. I really love your answer. I think that's great. I think for anyone doing, research, starting with a solid foundation is absolutely critical. And with that, I think I really enjoyed the fantastic discussion tonight, and thank you very much, everyone. Our speaker, Professor Mikos, and also our excellent panelists tonight. And so with that, I would like first to representing ICANX to deliver this virtual certificate to Professor Mikos. Thank you for delivering fantastic talk on our 130 ICANX talk today. Thank you very much, Professor Mikos.
Thank you very much for the great honor to be part of the ICANX talks.
Thank you very much. So as usual, please stay joining us for next week. We have our next week's speaker, again from University of Michigan, is going to talk about the chirality, complexity, and graph theory of nanostructures. And following on, also the last talk of the February will be delivered by Professor Raffaele Bassanti on colloidal chemistry. And also very exciting new addition to ICANX talks is our Tuesday Youth Talks. And so please do join us next Tuesday for the first Youth Talk on Valentine's Day. That will add a very special touch to that day, I guarantee you. So with that, thank you very much for joining us tonight, and I'll see you next time.
不再是奇迹，不再是幻想，此刻真感觉全世界离我鼓掌，不必太在意身旁惊奇的目光，可以点点头，可以放声歌唱。我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。I can。没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越 造奇迹。我拥有梦想，我希望看见所有骄傲的人旁，不再为曾经失败放弃或感伤，努力才是真的方向。I can，没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。I can， 没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。Yeah！ I can， 没有什么可以阻挡心中无限的力量。Oh yeah yeah I can you can， 你也能够像我一样飞越最高山岗。不再是奇迹，不再是幻想，此刻真感觉全世界为我鼓掌，不必太在意身旁惊奇的目光，可以点点头，可以放声歌唱。我创造奇迹，我拥有梦想，我希望看见所有骄傲的人旁，不再为曾经失败放弃或感伤，努力才是真的方向。